Good morning. Today we will discuss what is meant by a black body. And we will discuss the concept of black body radiation, which was tried to be explained by many scientists like Weins, Rayleigh, Jeans, and all. Those are classical times. And then there was some differences in what is seen experimentally and what these theories could come up with. And later, Max Planck explained the uh, black body radiation using his quantum theory. So we will see what is meant by a black body. See, from the name black body, you feel that that is something which is black in color. What is the peculiarity of black colored bodies? Why do we see something black? Can you tell me why we see something as black? When will we see something as black?
When the colors are, like the colors doesn't, I mean,
Come out of that. It absorbs
yeah.
out
No
of
light rays comes
It
from
absorbs
that
the
it.
object.
lights,
Yeah.
yeah.
So when light falls on a body and it absorbs all the light and it doesn't reflect any of the light, then we see it as black. So what is meant by a black body? A black body is a body which absorbs all the light. That's by nature. We know that that is seen as black. In physics, we can describe a perfect black body as a body that absorbs all the radiations, including the visible radiation, including light, ultraviolet, infrared, all the radiation. You have seen electromagnetic spectra, right? So a perfect black body is a body that attracts or absorbs all the radiations falling on it. And at the same time, if this black body is heated, it will emit all the radiations incident on it. So a very good absorber at a low temperature will be a very good emitter at a high temperature. So let us see what is meant by a black body in physics. A body which emits all the radiation incident on it. I didn't go to this definition of a black body in the beginning because we already have a concept of what is meant by black. So I wanted to come from that. So a body which emits all the radiation, which means it is a body that attracts or absorbs all the radiation. And when it is at very high temperature, it emits all the radiation. So such a body is called a black body. An ideal black body, when heated, radiates the radiation of all wavelength, visible and other wavelengths. So that is called a black body. Now, if you are asked to define a black body, you can tell that a black body is something which absorbs all the radiation at low temperature and emits all the radiations at high temperature. Now, can you think of something which will emit all the radiations, which emits a lot of radiations and which is at very high temperature?
Sun.
Star.
Sun, stars, so they are all examples for black bodies. Can you imagine we will call a sun a black body? So the name is confusing, right? But it goes well with the definition of a black body. So sun is an example for black body. All stars are examples of black body. And even the stove, stove emits a lot of radiation, heat radiations, uh, light, everything. So it's not a perfect black body, but still you can call it a black body. Then light bulbs, incandescent. So when electricity passes through that, it gets heated up and it emits radiations, a lot of radiation. So that's also a kind of black body, not perfect. And warm-blooded animals means our body, it gives away a lot of heat energy. So All of these bodies which emit radiations are black body with varying degree of perfection. If it can emit all the radiations, it is called a perfect black body. Or if it can absorb all the radiations, it's called a perfect black body. Now, the radiation emitted by the black body is known as a black body radiation. So, for a normal body, if A is the absorbed radiation, R is the reflected radiation, and T is the transmitted radiation, the sum of all will be 1, which means whenever a radiation is incident on a normal body, it is either absorbed, reflected back, or transmitted through it if it is transparent. So for a normal body, this is the case. The sum of all means whenever light or any radiation is incident, it will either absorb, reflect it, or transmit it. And the sum total is equal to 1 total. But for a perfect black body, either or when it is at low temperature, the total radiation is absorbed. A is equal to 1. Total radiation is absorbed. Excuse me. So we were discussing black body radiation, right? So for a perfect black body, the absorption will be 1, which means all the radiation will be absorbed and nothing will be transmitted at low temperature. And at high temperature, what happens is all the radiation will be reflected, nothing will be transmitted. So this is the case of black body. Now let us see what are the different ideas or theories related to black body. First of all, let me discuss Wien's displacement law. This is a law put forward by William Weins. And Wien's displacement law is not there in your textbook, but I think that it is worth discussing Wien's displacement law because I have seen in some questions related to that in your in your question papers, and also whenever you go for Wien's law, search that in the Google, the first thing that comes up is Wien's displacement law. So you are here with me, right? You are
Yes,
here with,
teacher.
yeah, okay. So let us see what is Wien's displacement law. Here you can see a graph. This is a graph drawn between the energy density and also the wavelength. Okay, at different temperatures. So Wien's displacement law states that the black body radiation curve for different temperatures will peak at different wavelengths that are inversely proportional to the temperature. Let us try to understand what it means. So Wien's displacement law states that the black body radiation curve. What is meant by black body radiation curve? It's a graph drawn between the energy density and wavelength. So we said that a black body will emit radiations. So we see that for radiations emitted at different temperatures, see this is the curve for a black body emitting radiations when the temperature is 3500 Kelvin. This is another curve where the same body will emit radiation when it is at 4500 curve. See here the wavelength. See, the same body at a lower temperature will emit. See, as the temperature increases, the amount of energy or the energy emitted by the black body also increases. But another relation which you can see here is that as the temperature is lower, the peak value or the maximum value of wavelength emitted, or not the maximum value, majority of the radiations emitted have a particular wavelength, which is called the peak. So the peak is a little towards the larger side of wavelength. Now, as you increase the temperature, see at 4000 Kelvin, this is the peak value of wavelength. And at 4500, a little bit more towards the 500. Now here at 5000, see, it coming little bit more towards the 500, that is maybe around 600. And here 5500, a little bit nearer. See, there is a trend here. So the wavelength, the peak wavelength which is emitted is slightly reducing as the temperature is increasing. This is Wien's displacement law. The wavelength is displaced towards the lower side as the temperature increases. Is that clear to you?
Sir,
Is
can
this,
you repeat again this part?
yeah, I told you that what is black body radiation curve? Is that clear? This is for one particular black body which radiates, give out radiations at different temperatures. See, this is the curve showing the energy or radiation energy emitted at 3500 Kelvin. This is another curve showing the radiations which is emitted when the same body is at 4000 Kelvin. See, when it is at 4500 Kelvin, this is the curve. Now, see, each of this line is drawn with a slightly different color. When the wavelength is large, what will be the color of light for a larger wavelength? Which
Red,
color?
right?
Red. As the wavelength reduces, what happens? It goes towards
Violet.
the blue side, light blue, violet side. So see, you know, VIBGR. So red means large wavelength, orange means a little lesser wavelength, yellow means a little lesser wavelength, green means little lesser wavelength. So as the temperature increases, the peak value of the wavelength, which means each body will give one prominent radiation. So majority of the it will give other radiations as well, but majority of the radiations given out will be in a particular wavelength. That is called the peak wavelength, shown by the peak in the graph. See, energy density. So majority of the radiation will be in a peak for a particular wavelength. That wavelength is called the peak wavelength. And this peak wavelength decreases with increasing temperature. That is Wien's displacement law. Or the wavelength, majority of the wavelength or the peak wavelength emitted by one body, one black body, is displaced towards the lower side when the temperature is increased, or the wavelengths or the peak wavelengths are inversely proportional to the temperature. Now, is it clear? Is it clear?
Yes,
Say yes or no.
teacher. Yes,
Say yes or
yes,
no.
teacher,
Yes.
clear. I
Oh,
said.
okay. Okay. It has been discovered by William Wein several years before Max Planck developed a more general equation. So this was discovered by William Wein. That's why it's called Wien's displacement law. Or you can say that the peak value of wavelength is inversely proportional to T, temperature. This is the absolute temperature. What is meant by absolute temperature? Absolute temperature means temperature measured in Kelvin. So if the unit of temperature is Kelvin, you call it absolute temperature. And it is usually represented by capital T. And if the temperature is measured in degrees Celsius, it is usually represented by small t or theta. And B is a constant which is called Wien's displacement constant. B is approximately equal to 2898 micrometer Kelvin. See, micrometer is the unit of length. That is the wavelength. And Kelvin is the unit of absolute temperature. So this is the value of Wien's constant, Wien's displacement constant. So the higher the temperature, shorter or
Teacher,
smaller air.
the temperature in denominator, right?
Temperature,
The temperature is in denominator, right? But it should be Kelvin per Kelvin, right?
B is equal to, see,
Okay.
temperature
Got
is
it.
in the
Yeah.
denominator.
Multiplication, right?
When it goes to other side, it goes multiplication. That's why. So the higher the temperature, the shorter or smaller the wavelength of the thermal radiation emitted by a body. Lower the temperature, the longer or larger the wavelength of the thermal radiation. And for visible radiation, hot objects emit bluer light than cool objects. I will tell you where this is more prominent, where we can see this idea more. This is seen in the case of stars. So when astronomers observe stars, they will be emitting a prominent wavelength, right? When they observe stars, they see different colored stars. If the color of radiation emitted by a star is bluer towards the blue side, then they say that that star is very hot. Now, if the radiation emitted by the star is towards the redder side or a reddish star, it's cooler compared to others. So we can look at the color of the star and tell the temperature approximately. This is the idea when it comes to stars, because we know that stars are black bodies, right? They emit radiation. So looking at the color of that radiation emitted by them, the astronomers can somehow tell it's a cooler star or a hotter star. So let me ask you one thing. uh, Bibi, what will be the color of a hotter star, comparatively hotter star? It will be bluish or reddish.
Teacher, can you repeat?
What will be the color of light emitted by a bluer star? Bluish, sorry. What will be the temperature of a bluish colored star?
Will be
It will,
hotter, right?
it will be hotter, right? So if a star is reddish in color, what about its temperature?
Cool.
It's comparatively cooler. So the anyway, you
Teacher,
know that all the stars are very hot, but within them the temperature varies. Okay. Now this
teacher.
is yes.
So can we compare with this? Like any object that emits blue color light will be a hotter object. Any object without having
Yeah. I
considering
will tell
star.
you if you have been to kitchen, the fire. Sometimes the fire is really blue in color. Sometimes it is reddish. I usually see that the fire produced by burning firewood at home, traditional uh, kitchen, you can see fire which is red in color. Now, with what we have is natural gas, right? When we heat, it's blue in color. Which has more temperature? That blue colored fire or the red colored fire? Those who are cooking will know better. The blue colored fire has, yeah,
Yeah.
blue
Teacher,
colored
teacher,
fire has
like the
temperature. Yeah,
computer and the laptop sometimes emits blue color light, right?
yeah. I don't
So
know.
that means that no. So I saw that there's some specs, for filtering the blue color light of the computer.
Uh,
Those who
yeah, maybe that is more dangerous. There may be that, but
because it's a
I
hot
don't know
object or
the real reason behind that. Real
out.
reason. See, we can touch the fire of a candle. If you are ever used a candle, you can touch. It's not that hot, but you cannot touch the fire produced, blue fire produced in a gas stove. It's very hot. So that you can see there. Blue fire is more hotter than red fire. Okay, so let us go. This is not in your textbook in this chapter, but later when you
So
learn
teacher,
about
we can compare sun and another star which is blue in color. So
yeah,
that blue colored star will be more hotter, right?
yeah, more hotter.
So what is the color of sun?
Sun, we see it. Uh,
We see it because of our atmosphere, right? Like we
yeah,
see
that
different
is
in
because
different
of
times.
our atmosphere.
Normally, I heard
The
sun
sun
is white
is a
color.
redder star compared to others. Sun is a younger star and it's a redder star compared to other stars. Reddish, more reddish than other stars. Of lesser temperature compared to the blue, very hot stars. Okay. So let us see the other. Oh, it's very hot. Sun is very hot for us because we are nearer to it. There are other stars which are much hotter, but we are farther away. We don't get their temperature. That's it. Now let us see the Wien's distribution law, which is given in your textbook in this chapter. So now we are going to see another law put forward by William Wiens. This is William Wiens, and this is called Wien's distribution law. Why I discuss Wien's displacement law and Wien's distribution law separately? Because usually when you search Wien's law, you will see Wien's displacement law and may get confused. Also, I have seen in one or two question papers how the absolute temperature changes with wavelength. So it's an inverse relation, so that you can just note it down. Now, Wiens compared the wavelength and for a particular temperature. For a particular temperature, this curve shows the pink dotted line shows the distribution curve as predicted by Wien's distribution law. Let us see what is Wien's distribution law. Weins law or Wien's distribution law is a law of physics used to describe the spectrum of thermal radiation. So this is the radiation emitted by a particular black body when its temperature, absolute temperature is 5800 Kelvin. And this is the energy density. And here along the x-axis, frequency is taken in terahertz. So frequency is taken along the x-axis. In your textbook, you will see a similar graph, but there along the x-axis, the wavelength is taken. Do you see any difference in the graph given in your textbook and I have shown here? I did that by purpose. You can see this green line is in this side, right? It looks like a mirror reflection of this graph. Did you see in the textbook? Page number 509. It's like a mirror reflection of this graph. You know that frequency and wavelength, they have inverse relation. Larger frequency means lesser wavelength. So in this graph, along the x-axis, you have frequency, but in your textbook graph, along the x-axis, you have wavelength. That's all, but the meaning is same. When Wien's law was first delivered by William Wein in 1896. So the law states that the energy distribution of black body is inversely proportional to the fifth power of wavelength. See here you can see the wavelength. Here E lambda d lambda represents the energy density of radiant heat within the limit lambda and lambda plus d lambda. Usually the way black body emits radiation of all wavelengths, but one particular wavelength will have maximum radiation. So that is called the peak wavelength. So we are considering only in that limit near the peak wavelength. So we are considering the energy density only in the limit lambda and lambda plus d lambda within that limit. When you consider the energy density, it's a complex relation. But what I want to note here is that, see, 8 pi HC lambda raised to minus 5 exponential of minus HC by k lambda t d lambda. Here you know pi. Here H is Planck's constant. But Max Planck didn't put forward his theory and Planck's constant at this time. So the original theory or original Wien's distribution law doesn't contain Planck's constant. He just told that the energy distribution is inversely proportional to the fifth power of wavelength, lambda raised to minus 5. So you just have to note here that the energy density is inversely proportional to lambda raised to 5. That's all you have to note. Don't get moved by this complex equation. Forget about that. Wien did not put forward these constants, these values in his original equation because H or Planck's constant was not discovered then. Is that clear to you? You have to focus only on lambda raised to minus 5. The energy density varies as lambda raised to minus 5. And Wien said that the energy distribution of black body is inversely proportional to the fifth power of wavelength. And the equation does not accurately describe the short wavelength or high frequency spectrum of the thermal emission, but it fails to accurately does okay fit the experimental data for long wavelengths or low frequency. Let me explain that. Here you can see the blue line is the experimental value or the actual value observed through experiment. The pink line, pink dotted line, is that predicted by Weins law. Here you can see at the high frequency side, see the pink line and the blue line exactly coincides, which means the Wien's distribution law can clearly explain whatever experimental quantity was obtained at high frequency side, which means smaller wavelength side. It accurately explained the experimental value. But when we come to the low frequency region, that is low frequency means high wavelength region, it doesn't match with the experimental value. See, there is a discrepancy here. It's not exactly matching. Is that clear to you?
Yes, teacher.
So Wien's distribution law could not exactly explain the radiation curve for a wave. It can explain the radiation curve towards the high frequency side, that is lower wavelength side, but not at the small frequency side or larger wavelength side. So this is it. So what is Wien's displacement distribution law? Wien's distribution law states that the energy density of a black body radiation is inversely proportional to the fifth power of wavelength. But Wien's displacement law can explain the experimental values got for the high frequency region or low wavelength region. But it could not explain the values experimentally got for the low frequency region or the higher wavelength region. Is that clear?
Yes, teacher.
Okay. Now let us see, here you can see Rayleigh genes, right? So let us see a similar law later put forward by two scientists, Rayleigh. This is Lord Rayleigh and this is Jeans, James Jeans. So Lord Rayleigh and James Jeans put forward the Rayleigh Jeans law. It said that the energy distribution of a body is inversely proportional to the fourth power of wavelength. So this is the law or equation put forward by Rayleigh and Jeans. Here again E lambda D lambda is the energy density of the radiation within the limits lambda and lambda plus D lambda. And 8 pi k, k is Boltzmann's constant. T is the absolute temperature, and lambda raised to -4, which means inversely proportional to the fourth power of wavelength. Now, Rayleigh also put forward this law before Max Planck's quantum theory, and it is consistent with the experimental results for the long wavelength, that is high frequency consistent with the long wavelength means high frequency region, but it is not consistent with the experimental results for the small wavelengths. See here, can you guess along the x-axis it is frequency or wavelength?
Wavelength.
Wavelength. See, it's just the mirror reflection of the other curve. So just I wanted to show you the difference by both graphs. And along the y-axis, you have energy density. So the time is going to